Welcome to today's presentation entitled Introduction to Noise Metrics, Irish EPA Noise Guidelines and UK Assessment Standards. Just to give you a brief introduction, my name is Diarmuid Keeney. Our company is ICAN Acoustics and our website is located at www.acoustics.ie. I hold an MSc in Applied Acoustics from the University of Derby. I also hold a diploma in Acoustics and Noise Control from the University of Ulster, and as well as that, a Bachelor of Engineering from the National University of Ireland. Below, I've listed a number of our clients throughout Ireland. Okay, here are the topics we plan to cover today with you. Firstly, I'd like to give you an explanation of the standard planning and noise enforcement metrics used here in Ireland. Secondly, I'd like to give you an understanding of the decibel scale. Thirdly, I'd like to touch on the Irish EPA noise guideline metrics. Fourthly, I'd like to also touch on one UK assessment standard, namely BS4142. And finally, I'd like to also give you some practical noise measurement advice. Okay, what is noise and what is sound? Noise, in its simplest form, can be described as unwanted sound. Sound, on the other hand, is a result of a propagating disturbance through a physical medium. For example, sound waves travelling through air, or vibration through a solid. Sound is measured in units of decibels, dB. It's very important also to note that dB is not unique to sound. For example, voltages can be measured in dB. The length of your hair can be measured in dB, or the height of a building. They can all be expressed in dB. So for example, when you see something written as 50 dB, it means nothing on its own. While if you do see something written as an LAeq equal to 50 dB or 50 dBA, that does mean something. So why use the decibel at all? Well, 0 dBA starts at the threshold of hearing. The decibel is used to deal with huge variations in sound pressure level between the threshold of hearing and a given sound pressure level. So rather than quoting pascals, pressure level differences are much easily expressed using logarithmic ratios. The table below describes how various decibels might sound to you. On the column on the left you can see the level as expressed as a dBA level, and on the right you've got the description of the sound. So you can see 0 dBA is approximately equal to absolute silence, 25 dBA typically what you would expect in a very quiet room, and various other levels all the way along there. For example, 85 dBA might be the level you'd expect in a very busy pub, where your voice may have to be raised to be heard. So there are just a few examples of different levels. This slide deals with the perception of sound. A 10 dBA increase in a noise level is perceived to be an approximate doubling of loudness. A 20 dBA increase in noise level is perceived to be an approximate quadrupling of loudness. So here are some rough rules of thumb in relation to dBA levels. A 1 dBA change may be just noticeable. It's about the smallest perceptible change that a human can recognize. A 3 dBA change, on the other hand, is noticeable. A 5 dBA change is what's described to be of marginal significance, and a 10 dBA change is significant. We know from above that a 10 dBA increase in a noise level is perceived to be an approximate doubling of loudness, while a 10 dB reduction in noise level is perceived to be a halving of loudness. This slide deals with LAeq or dBA. Essentially those parameters are the same. This is a general descriptor of environmental sound exposure. I'm going to explain the principle of an LAeq using a graph below. If we look at this graph, on the vertical axis here we've got SPL, which is sound pressure level. On the horizontal axis we plot time. So if we set up a sound level meter, for example, and start to record the sound pressure level, we'll notice over time that it's varying in level. So for example, if you think of a number of vehicles passing, you may have vehicle events that are creating increases, and then you have decreases and so on. So sound pressure level in many cases can vary considerably over a time period as that of the area under the curve. So it's a way of dealing with sound pressure levels that are ever changing in many cases and expressing them as a single figure, and that is essentially a single equivalent continuous level. So we look at that straight line along there, for example. That's essentially what an LAeq is. So although you're measuring variations in sound pressure level that are changing over time, the principle behind an LAeq is you're coming up with an equivalent continuous level, and that straight line level there replicates an area that is equivalent to the area under that jagged line. So essentially that is what an LAeq is. Here are some metrics you need to know. In the previous slide we dealt with the LAeq or dBA level, which is essentially an equivalent continuous sound pressure level, and it normally has an A weighted applied to it. There is another parameter, however. It's called the LA10, and this is a measure of the noise level exceeded 10% of the measurement time. In the UK, this was used to determine the eligibility for sound insulation grants, for example for traffic noise or indeed for aircraft noise and so on. If I was to plot an LA10, for example, you may see a line, a horizontal line, above that of the LAeq. The LA90 is a measure of the noise level exceeded 90% of the measurement time. This is widely used as an indicator for background noise level measurements. Again, if I was to plot that on the graph, you may see a level below that of the LAeq, shown in the blue line below. Then the all-important time interval. As I said to you, you need to consider your measurement time, which is important. So essentially you have sound pressure levels ever changing as time progresses, but it is very important that you note the time period which the measurement was conducted. So for example, here is an example of an LAeq. Typically expressed like that. You'll have an LAeq, 1 hour equal to 55 dB. So that's essentially a measurement of the LAeq conducted over a 1 hour long time period. This also could be expressed as 55 dBA over 1 hour. Here is an example of an LAeq, a 16-hour LAeq, shown at say 62, or it could be expressed as 62 dBA over 16 hours. Again, you can express an LAeq over an 8-hour period. So for example, you may have LAeq 8-hour equal to 38 dB, or you can have LAeq night equal to 38 dB. So it is important to consider the time interval along with the sound pressure level measurement. This slide deals with general Irish EPA limits. Looking then at IPPC licensing and noise, within that there is a guidance note in relation to scheduled activities, and this document contains suggested noise limits of 55 dBA for the daytime and 45 dBA for the nighttime, with the said limits to be applied to sensitive locations. Whilst these limits have a very specific application, they have appeared in many different contexts and often form the basis of conditions in planning permissions set by local authorities, for example. It is important to note that these are absolute limits, and they are set at the boundary of the premises or at the nearest noise sensitive location. And please note that absolute is highlighted in red. I'll come back to that later. It is important to note also that some of the features of a noise may warrant a tonal penalty. So if a noise is tonal, for example, or has an intermittent nature, or indeed it may even be impulsive, you could end up with a situation where you need to apply a +5 dB penalty. So if you think of a situation where you can measure 50 dBA of factory noise, say at a residential property, if that factory noise has a tonal quality to the noise, you may need to apply a +5 dB penalty, and that will result in an LART of 55. An LART is essentially a rating level. It's an A-weighted level, but it has a rating applied to it, a plus 5 dB penalty applied to it, creating a rating level of 55. So while the measured level is 50, a plus 5 dB penalty is added. Okay, very often with planning conditions you can have a situation where a noise limit is specified at the boundary or at the nearest noise sensitive location. Here's an example in the centre of Dublin. You have a situation where you've got a commercial development here. I'll show you on screen with the mouse. And essentially on the boundaries you have residential properties along here and essentially along here. So I've denoted the boundary, the red line there, for example. Now in a situation like this, you may have a limit specified at the boundary or at the nearest noise sensitive location. It would be normal to specify it on a boundary, somewhere like a location there shown at one particular spot, if you like, and that's a boundary level. So in a case like this, the residential property is relatively close to the boundary anyway. So in a situation like this, you may have a limiting value of 55 dBA at the boundary or at the nearest noise sensitive location. Essentially, however, you would consider a boundary level here as being more appropriate. On our next example then, the necessity to specify a limit of 55 dBA in a situation like this on the boundary is a lot less. For example, there's little point in specifying a level of 55 dBA at this boundary, for example, because the residential properties are some distance away back here. So in a case like this, is it necessary to have 55 dBA on this boundary? I would say no. Even if the level, for example, at this location was somewhere in the order of 75 dBA, that wouldn't necessarily matter, because essentially back at the residential properties over here, your level may be at 55 dBA. So again, it's important to distinguish between a level that's set on the boundary or at the nearest noise sensitive location, and that's why there are two options. It's an either or situation. Okay, moving on then. Okay, this slide deals with noise modelling. This is an example of a 3D noise contour model. If you take a look at the central location here in the image, and we have a number of noise sources modelled within a facility. This facility happens to be a recycling facility, a metal recycling facility. So essentially we can introduce noise sources into the noise contour map and essentially look at how they behave. These levels along here, for example, they are predicted LAeqs. So for example, at that property, the noise level there is likely to be 52 dBA, or indeed an LAeq of 52 dB. So essentially you can predict the noise levels at all of these properties. These contours then essentially relate to a specific sound pressure level. So using the key here on the side, you can work out the likely level at each of those noise contours. So if we take red there, for example, essentially if you see red, the level is in excess of 60 dBA. So again, you're looking at a level of 60 dBA here and so on. So you can examine how it's going to behave over distance. You'll notice as well the buildings here, for example, there's a bit of shadowing going on behind them. So the building barrier effects results essentially in lower sound pressure levels behind the building. Moving on then to our next slide. Okay, this is a close-up of the site we just looked at. And in here you can see the individual sources being modelled. Now it is important to note that you can also model barriers around a particular site as such to look at their effectiveness. And again, being close up, you can see how the sound pressure level varies around a building. This is a building here, for example, so you can end up here with a sound pressure level of 60.1 dBA, and then at the other side of that building it's 46.7. So you can look at the building barrier effects and how they're likely to impact on the noise level as well. This slide shows a noise contour model. Essentially this is a 3D image of a modelled site. Here we have a barrier or a high level wall along the that particular boundary, and again these are lower walls surrounding the boundary. We can model any source and predict the likely level at any of those properties, and those spheres that you see there are they're essentially reception points, so we can predict the noise level at any of those locations. Okay, moving on then to the current EPA guidance documents on environmental noise. One of the documents you could refer to is the Environmental Noise Survey Guidance document. It was issued in 2003. Another document then would be a guidance note for noise in relation to scheduled activities, and there is a second edition of that which was issued in 2006. Another document worth looking at also is a document titled NG4, and this is currently out for consultation, and it's essentially a guidance note for licensed IPPC applications, surveys and assessments in relation to scheduled activities. Also, there are a number of other EU guidance documents that were produced for noise mapping purposes as part of the EU Environmental Noise Directive. There's also guidance on noise assessment of wind turbines at EPA licensed sites, and that document is titled NG3. Okay, in this slide we move on to BS4142, and this is essentially a British standard that deals with the assessment of industrial noise in a residential area. Now for this slide I'm going to work through an example for you. It is important to note that the EPA guidance documents do refer to the UK's BS4142, so it does have relevance here in Ireland. I would describe this as an excellent standard with a good correlation with the likelihood of complaint for a given mixed industrial and residential arrangement. One of the benefits of this document is that it uses relative limiting values. Okay, here is a worked example of BS4142. Suppose we were to measure the noise from a facility with the facility running at a noise sensitive location, and then we shut that facility down temporarily to conduct a second measurement, and from that we could derive the specific noise level. So suppose we calculate the specific noise level to be 55 dBA. Now, when we measure this noise, suppose we note that there is an impulsive nature to the noise, or it may have a tonal component, then we would add a plus 5 dB penalty to that. Now that would give us a rating level of 60 dBA. So essentially you take the specific noise level, if there's a 5 dB penalty to be applied, you apply it, and that gives you a rating level of 60 dBA. Then we take the rating level and we subtract the background level. And suppose we do that, we take 60 dBA and we subtract 40 dBA from that, and that gives us a level of 20 dB. So what BS4142 states is that a difference of 10 dB or more indicates the complaints are likely. If we were to find, however, that the difference was approximately plus 5 dB, then this would be of marginal significance and complaints would be possible. In this particular case we've got 20 dBA, so it is a positive indication that complaints are likely. However, if that change or that difference was only 5 dB, complaints would be possible. So the third possible outcome then is that if the rating level is more than 10 dB below the background noise level, and this is a positive indication that complaints are unlikely. So this is the third scenario. So essentially when you carry out a BS4142 assessment, you have three possible outcomes. Outcome number one is that complaints are likely. Outcome number two is that complaints are possible. And outcome number three is that complaints are unlikely. Okay, the all-important character of a noise. Sounds with an identical dBA level, they may differ considerably in their capacity to cause annoyance or disturbance because of the character of the sound. And this is an important point. Generally, sounds containing a distinguishable tone are more noticeable and potentially more annoying than sound without such features. So that's why, for example, in some assessment processes, you would apply a plus 5 dB penalty to a source that had a tonal component. This slide deals with tonal noise. On this slide I have two spectra. The one on the right is essentially a noise measurement, and each of these, if you like, it very much looks like a histogram as such, but these are third octave band measurements, and if you look at those measurements, you'll see that there's energy in all of those third octave bands. That would be described as broadband noise. Now, looking on the graph on the left, for example, the difference between those two, there is an elevated third octave band. Now it's quite likely in a situation like that that you have a tone within that 160 Hz band. So that tone could be, say for example, at 158 Hz. However, its impact is causing the third octave band to be elevated. So in a situation like that, very often you'll have a tonal component contained within that 160 hertz band. So that's how we would discern if something is tonal or not. So there is a whole assessment criteria associated with that. So when it comes to tonal noise, there are various standards and methodologies used to determine if a noise is tonal or not tonal. The EPA guidance documents refer to ISO 1996, which were issued in 2007, and essentially, using a third octave analysis, you can determine if a sound has a tonal element or not. Now, there are many other techniques also available to use, for example, one of them being the joint Nordic method. This slide deals with sound propagation. The most important factors affecting noise propagation are the type of source, whether it's a point source or a line source. It could be a planar source. Another factor is the distance from the source to the receiver. Another example would be atmospheric absorption. As sound passes through the air, different frequencies are absorbed at different rates. A good example of this is older foghorns that were used for navigational purposes often emitted a low frequency tone for the simple reason that low frequency sounds are less susceptible to atmospheric absorption, therefore they travel further. So this was important when it came to navigation. You wanted to generate a low frequency tone that travelled a long distance. Another factor that affects sound propagation is wind. Essentially, if you're downwind of a source, the noise level is typically higher. If you're upwind of a noise source, the sound level is typically lower. Another factor that can have an impact on sound propagation is the temperature, or indeed the temperature gradient, and there are all sorts of temperature inversion effects that can affect sound levels between a source and receiver. Another factor to consider are obstacles such as barriers and buildings. We saw in the noise contour model earlier that buildings can create a shadowing effect. Another factor to consider is ground absorption. Reflections can also have an impact, and of course humidity and even precipitation. This section deals with practical measurement advice. Below we have a graph of some unattended noise measurements we conducted in Dublin inner city near Trinity College, where we logged the sound pressure level as well as the weather. Now, one important note on this graph is that the background noise level is often considerably lower during the nighttime period, and you'll notice as time progresses, you have 6 o'clock in the morning, 7 o'clock in the morning, you'll have more activity, the background noise level raises, it gets higher, and essentially evening time it starts to fall off again back to the nighttime period. So what is important is the background noise level is ever changing at any site. So depending on the time of measurement, it can have an influence on the actual background noise level measured. So for example, if I was considering something that was going to run 24 hours a day, I would be very interested in the lowest background noise level observed over that 5-day period. If you're going to assess the noise, you need to know the effect of that noise when the background noise level is as low as 38.5 dBA. It's very important when conducting unattended noise measurements that they also include weather logging. On the picture on the right here, you have a typical weather station that will gather information for you, like the wind speed, for example, the wind direction. You've got a rain collector here, essentially, where you can measure the rainfall, humidity, and all sorts of parameters relating to the weather. So they are captured simultaneously along with your noise level, so you can correlate a specific sound pressure level measurement, and that is an important part of any noise assessment. This slide deals with the effects of wind on a noise source. For example, if you consider this situation where you have wind travelling in this direction, you have an industrial facility here, for example, where noise is radiating essentially in all directions, if you like, but the effect of the wind results in a situation downwind of that source where the sound pressure level is higher. And if you measure upwind of that source, the sound pressure level will be lower. So it is important to note the wind direction and of course the wind speed to look at how it impacts on your measured level. To replicate a worst case scenario, you should be measuring downwind of a source. This slide deals with some practical measurement advice. Ideally, noise measurements should be conducted in neutral weather conditions in the absence of wind or rain. Now that can be difficult in Ireland, but it is important to wait until you have situations where you've got calm wind conditions and ideally no rain. Another important point to note about rain is that when roads are wet, traffic noise can be considerably higher at a site. So if you're measuring a background noise level, you would need to do that at a time when roads are not wet. It's important also to use instrumentation that holds calibration certification from an accredited independent test house. Ideally, this should be Type 1 equipment or Class 1 equipment. All instrumentation should be calibrated before and after a measurement period to monitor instrument drift. So essentially, using a field calibrator, you conduct a calibration measurement in advance of your measurements, and then you conduct a second calibration measurement just after your measurements to see if there's been any drift in the instrumentation. Many of the guidance documents suggest that measurements should be conducted in wind speeds below an average of 5 meters per second. For outdoor measurements, all instruments should have a windshield fitted. A suitably competent person should be used to conduct a noise survey, and that's contained within the EPA Guidelines. Okay, the topics we've covered today. Hopefully I've given you an explanation of the standard planning and noise enforcement metrics used here in Ireland. Secondly, I hope to have given you a better understanding of the decibel scale. Also, we touched on Irish EPA noise guideline metrics. We also examined one UK assessment method, namely BS4142. And finally, I've given you some practical measurement advice. Okay, so what are the next steps? Essentially, we have a free checklist that you should use before conducting any environmental noise survey. And if you'd like a copy of that, please email me at diarmuid@acoustics.ie. So if you have a specific project you wish to discuss, from outside Ireland you can contact us at ++353 1 4403 869. From inside Ireland you can contact us at 01 440 3869. For more information, see www.acoustics.ie. Again, I'd like to thank you for your time, and I'll leave my contact details on screen.